You are watching AI Paperslop, our YouTube series where we summarize AI and tech papers. Today, we are doing a deep dive into ProLong. Programmatic memory enables long-horizon reasoning by Alexis Fox and the team at Duke University.
Yeah, and the core insight here is something, honestly, every ML engineer and AI builder needs to hear right now.
Exactly. I mean, we all know LLM agents struggle with long-horizon tasks, right? Mostly because of context rot and this thing called the Fidelity Tractability Tradeoff.
Right, and ProLong basically solves this by just ditching complex memory heuristics entirely.
Yeah, it throws away the vector databases, the summarization loops, all of that. Instead, it losslessly appends every single action, observation, and score into one massive text log.
And then it just lets the agent use programmatic tools, specifically Python and grep, to search that log.
Which is wild. And it works. It improves performance on the ARC AGI benchmark by 18 percentage points over a base coding agent.
It matches or beats state-of-the-art specialized harnesses like World Modeler and Schema, too.
And it does all of this using up to 5.8 times fewer tokens. So let's get into why throwing away sophisticated vector DBs might actually be the key to long-horizon agentic reasoning.
Yeah, it's a massive paradigm shift in how we approach agentic memory. But to, understand the gravity of those numbers, we really need to look at the testing ground the researchers use.
Right, the ARC AGI benchmark.
Exactly. This is a continual learning benchmark that is basically designed to break agents. They're dropped into these 64 by 64 pixel grid games, but they are completely blind to the rules of the environment.
So they have no idea what they're supposed to do.
None. The agent has to infer the physics, the mechanics, the objective, all of it, entirely through trial, error, and exploration.
And what makes this even more brutal, I think, is that they aren't using vision language models for this, right?
No, not at all. The 64 by 64 grids are fed to the model as raw ASCII text.
Which is, that's essentially forcing a language model to do complex two-dimensional spatial reasoning using a one-dimensional sequence of characters.
Yeah, it's hard enough for an LLM to understand a single static ASCII room, let alone track how that room changes over 2,000 discrete actions.
So our mission today is to figure out why the solution to that massive cognitive load is actually a step backward in complexity.
Right, why a giant text file and basic bash tools might be the holy grail here. And I think the best place to start is the root cause of the problem, which is the fidelity tractability trade-off.
The fidelity tractability trade-off. Yeah, break that down for us.
So if you look at the architecture of current LLM memory systems, frameworks like MEM0 or MEMGPT or SkillRL, they operate on a fundamentally lossy premise.
Right.
They manage an external memory store through read and write operations. Because context windows have traditionally been expensive and, constrained, the write operation relies on heuristics.
So the system has to use compute to evaluate the current state and basically guess what information is worth saving.
Yeah, exactly. It might compress the last 20 observations into a short scratchpad note, or summarize a movement trajectory, or try to distill a sequence of actions into a generalized skill.
So you compress the data at the right stage to make the read stage tractable, because you just dump every single frame into the active context window.
You blow past your token limits, or worse, you hit that lost in the middle phenomenon where the model's attention mechanism just gets totally overwhelmed by noise and it forgets the prompt instructions entirely.
Right, but the vulnerability there is that reducing what you save inevitably discards granular atomic details.
Exactly. In a long horizon exploratory environment, a seemingly irrelevant detail on turn 2, say a specific block changing from red to blue when you move past it, that might actually be the core mechanic required to solve the puzzle on turn 400.
Oh, wow. Yeah.
But if your heuristic decided on turn 5 that the color change wasn't important and it summarized it out of the scratchpad, that information is permanently destroyed. The agent is flying blind and it doesn't even know it.
I was thinking about this in the context of debugging a complex distributed system. Imagine a massive server crash. To find the root cause, you need to hunt for anomalies.
Right.
If you hand me a high-level executive summary written by a junior engineer that just says, servers ran hot at 2 p.m. then failed, that is useless to me.
Completely useless.
I need the raw, unfiltered system logs and a powerful search query tool. You don't know what specific error code you're looking for until you actually understand the shape of the crash.
That's a perfect analogy. You cannot filter for relevance before you know what is relevant. And this is the exact philosophy behind the ProLong architecture.
So they designed it around 3 rigid pillars, right?
Yes. First, absolute simplicity. The right operation uses 0 learned heuristics.
Yeah.
No LLM calls to summarize, no embedding generation.
Just raw logging.
Exactly. Second is losslessness. Absolutely nothing is compressed. It is a faithful ground truth record of every single state. And third, coding agent compatibility.
Meaning, instead of building semantic search layers, you just give the agent native coding tools to query its own history.
Right. But I know what you're thinking.
Yeah, this raises a massive red flag for anyone who has ever managed an API billing account.
Yep.
If we are saving literally every single action, every 4,000 character ASCII grid, and every score change into a text file over thousands of turns, aren't we just creating the exact context rot we were trying to avoid? I mean, we'd be feeding the model millions of tokens per turn.
And that's where the paper makes a crucial technical distinction between accessed context and accessible context.
Okay. Access versus accessible.
Yeah, the access context is what lives inside the LLM's active context window during a specific inference call.
Right, so that's your system prompt, the latest board state, maybe the standard output of a tool the agent just ran.
Exactly. That accessed context stays highly constrained, usually capped around a few thousand to maybe 100,000 tokens. It is pristine and manageable.
So the model is never actually reading the entire history at once.
Never. The massive history is the accessible context. In ProLong, this takes the form of a file literally named logs.txt, which sits inside a secure, sandboxed container.
And that file can easily grow to over 10 million tokens in a single run.
Easy. The write operation simply appends a structured entry to the bottom of logs.txt for every turn. It logs the action number, the current level, the score, the agent's stated plan, the action it just took, and the resulting ASCII grid.
Okay, so how does the agent actually read it?
It accesses that massive file by writing code. It might write a Python script to search for, say, the last time the score increased, execute that script in the sandbox, and then only the script's output is passed back into the LLM's accessed context.
Wow, so it is querying a database, but the database is a raw text file, and the query language is Python.
It's elegant.
It really is. And because they aren't relying on complex memory abstractions, the system prompt is shockingly small, right?
Oh, yeah. We are talking about a minimal, roughly 30-line system prompt, basically just telling the agent how to use its tools.
Contrast that with the state-of-the-art baseline in this paper, World Modeler. That harness requires a 600-line prompt instructing the agent on how to build and update a Python simulator.
And it spins up multiple sub-agents just to handle frame pre-processing and animation.
Right. But ProLong operates without sub-agents. It's one agent, a 30-line prompt, and a text file.
So the natural question is how this minimalist approach holds up against those heavily engineered harnesses on the public set.
And the results are highly compelling. Though we should probably clarify that the benchmark uses a metric called relative human action efficiency.
Yeah, that's important. It evaluates an agent not just on whether it solved the level, but on how many actions it took compared to a human baseline. It aggressively punishes thrashing and random walks.
Makes sense. So let's run through those numbers. They tested this on frontier models with a 500 action limit per run. With Codex, which is their GPT 5.5 setup, ProLong hits a 41.2% pass-at-one score.
And pass-at-one meaning the agent successfully beats the environment on its very first attempt.
Right. Now, the prior top harness for that model was World Modeler at 45.1%. So it trails slightly on the first attempt, but when they swap the underlying model to Claude Opus 4.6, ProLong hits 42.4% pass-at-one.
Which establishes a new public state-of-the-art for that specific model, actually beating Argentica.
But the true endurance test comes from the Fable 5 evaluation, right?
No, absolutely. They extended the limit to 2,000 actions. Managing state over 2,000 actions is notoriously difficult.
Yeah.
And under those conditions, ProLong achieved an astonishing 97.4% best at 2 score.
That's massive. And for those running evaluations, best at K means the agent is allowed K independent attempts at a task, and it only needs to succeed on one of those runs to get credit.
Hitting 97.4% on best at 2 shows incredible reliability once the agent is actually allowed to explore.
And this brings up my favorite part of the paper, which is the token economics. Because as builders, performance is critical, but if the architecture bankrupts you in inference costs...
It never leaves the lab.
Exactly. ProLong uses between 4.2 and 5.8 times fewer build tokens than the specialized harnesses.
Let's put real dollars on that Fable 5 run. Achieving that 97.4% score cost the team a total of $1,750 in API credits.
Okay, and the baseline.
The prior state-of-the-art harness schema cost over $6,400 to achieve a similar result. Across the entire IRC AGI Benchmark suite, ProLong saved roughly 400 million tokens.
That is wild.
It really highlights a fundamental inefficiency in how we've been designing multi-agent harnesses. When an agent spends thousands of tokens constantly rewriting summaries of its past actions, updating internal vector stores, and passing lengthy messages back and forth between 4 different subagents,
The cost scales exponentially.
exactly. With ProLong, the right cost is almost negligible. It's just the compute required to append a few hundred characters to a text file. The recost is only incurred when the agent actively chooses to execute a grep command or a Python script.
And it only pays for the tokens in the query output, not the entire 10 million token log. I want to circle back to the metrics for a second. We threw out pass at 1 and best at 2. Why is there such a massive focus in this specific paper on best at metrics? Why not just measure the first attempt and call it a day?
It really comes down to the mechanics of exploratory games. In ARC AGI 3, the environments are completely opaque.
Right.
So the variance between independent runs is incredibly high because an agent might stumble onto the correct dynamic by pure luck on its first run and then get completely stuck testing a dead-end hypothesis on its second run.
Okay, that makes sense.
The authors demonstrated that a pristine, complete memory drastically expands the overall set of games an agent is capable of solving across multiple runs. Using GPT 5.5, the pass at 1 score was 41.2%, but the best at 5 score skyrocketed by almost 19 points to 60.1%.
Wow. So that proves the bottleneck isn't the model's reasoning capacity. The model is smart enough to solve the puzzle.
Exactly. The bottleneck is exploration variance. A flawless memory ensures that once it finds the right thread, it doesn't lose it.
So how is the agent actually thinking here? How does it parse this giant log? Because the authors ran an ablation study where they systematically stripped away the agent's tools to isolate what was driving the performance, right?
Yeah, and this peers directly into the black box of agent behavior. The tool ladder ablations validate the entire premise. If you restrict the ProLong agent to only read access, meaning it can only view chunks of the text file without advanced search, it scores a dismal 23.1%.
It simply cannot manually parse that much information.
Nope.
But then you give it grep and regular expression search.
And the score jumps to 27.2%. It now has the ability to filter the log for specific score changes or retrieve specific previous board states based on text patterns.
But the massive leap happens when you add Python access, doesn't it?
Oh, yeah. The score rockets up to 38.3%. The agent is now writing functional scripts to programmatically loop through its own history, calculate deltas between states, and model trends.
And the kicker for me is the final step of the ablation. When they reintroduce the write and edit tools, giving the agent the ability to make its own notes, write its own summaries, and maintain an active scratch pad.
The performance barely moves.
It goes from 38.3 to 41.2%. The ability to write notes to itself is almost statistically irrelevant as long as it has a perfect, searchable ground truth log of the environment.
Which challenges the MemGPT philosophy directly, An agent does not need to spend compute writing a summary for its future self if its future self is capable of writing a Python script to query the raw data dynamically.
The researchers proved this definitively with their workspace persistence experiment, too.
Oh, that was a brilliant experiment.
They took the base coding agent, the standard baseline without ProLong, and they maliciously wiped its sandbox workspace clean every single turn. Any text file it created, any summary it saved was just deleted.
And that base agent lost 4 full points of performance, dropping to around 19.9% because its entire cognitive strategy relied on passing notes to itself.
But when they wiped the workspace for the ProLong agent every turn, it only lost 0.5 points of performance. It was entirely unfazed.
Because it didn't need to leave itself post-it notes, the environment was already appending the unvarnished history to logs.txt.
Right. So grounding this in specific game mechanics makes it much clearer when programmatic memory actually provides an advantage. Let's take a short horizon game like 209.
Yeah, this is effectively a color matching puzzle. The current ASCII board tells you almost everything you need to know to decide your next move.
In this scenario, both the baseline agent and the ProLong agent perform well. The logs are short, they clear the level in a couple of hundred actions, and having a Python searchable history doesn't really offer a significant edge.
But then you drop the agents into a long horizon nightmare like G50T.
Oh man, this game. This game mechanic requires you to control a character, and when you execute a specific action, the game rewinds time and creates a ghost clone of your character that repeats your exact previous path.
And to clear the later levels of that game, you have to precisely coordinate multiple past versions of yourself, timing their movements across the grid so they hold down different switches simultaneously.
It is literal spatial memory torture, even for a human.
Oh, absolutely. For this game, the individual ProLong run logs exceeded 320,000 lines of text.
320,000 lines.
Yeah, the baseline agent completely failed. It simply could not hold the sequence of ghost movements in its active context. But ProLong scored up to 56.3% on this game with GPT 5.5.
Wait, how did it parse 320,000 lines, though?
The agent literally wrote a Python script to ingest those 320,000 lines, extract the exact integer step counts for every ghost path, and mathematically calculate the precise timing needed to trigger the final switch.
That is unreal. It offloaded the memory task to the machine.
It did. Which brings us to the most remarkable emergent behavior documented in the paper. It occurred in a game called Mail Suro.
Ah, yes. This is a complex maze, where the agent must control two separate blocks simultaneously, navigating them toward a goal while flipping switches that dynamically alter the maze walls.
The baseline agent scores about 34% on this. It wanders around, gets trapped behind a wall, and thrashes until it hits the action limit.
But ProLong scored 100% across all 5 of its evaluation runs.
Yeah.
And the mechanism behind that success is just staggering.
It really is. The ProLong agent, completely unprompted by the researchers, realized it could not just guess the path.
Right.
So it opened a new file in its sandbox and spontaneously wrote its own transition model in Python. It coded a simulator of the game's physics based solely on what it had observed in the logs.txt file.
Wait, it wrote its own physics engine?
Yes. It defined state variables for the walls and switches, mapped the 2D maze layout from the ASCII data, and then it executed a breadth-first search, a BFS algorithm, over the joint positions of the two blocks.
And a BFS algorithm explores all possible moves layer by layer, guaranteeing it finds the shortest path.
Exactly. The agent used this to calculate a valid route to the goal that was more than 50 steps long.
But it didn't just blindly trust its own code either. Before it executed that 50-step plan in the actual environment, the agent wanted to verify that its internal Python simulator was accurate.
Right. It wrote a secondary testing script, which it named regress.py.
It pointed regress.py at the giant logs.txt file, extracted the historical states, fed the previous state into its custom physics engine, and then wrote an assertion to ensure that its simulator's predicted output perfectly matched the actual historical board recorded in the log.
It built a physics engine, wrote unit tests for it, and validated those tests against its own lossless memory.
I mean, that forces us to reevaluate how we define and build agentic reasoning entirely. We spend immense resources trying to force language models to perform internal reasoning, designing massive chain of thought prompts to coax them into holding state within their neural activations.
And ProLong suggests that if you just provide a frontier coding model with a pristine, lossless external state and a Python interpreter, it will externalize its reasoning. It will construct the specific cognitive architecture it needs on the fly, tailored entirely to the physics of the environment it finds itself in.
So for the engineers and researchers listening, the takeaway here is a massive paradigm shift. Stop trying to build complex, lossy memory architectures. Stop trying to predict what your agent will need to know tomorrow by forcing it to summarize its thoughts today.
Supply them with a pristine log of everything that has occurred. Do not compress it. Let it scale to 10 million tokens in a text file. Then leverage the native coding abilities of these frontier models to query it.
The infrastructure is already there. grep works, Python works. Let the model write the query it needs exactly when it needs it.
It is significantly cheaper in terms of API costs, it is faster to deploy, and it achieves state-of-the-art results without needing 600-line system prompts or 4 different subagents constantly debating over what an ASCII pixel represents.
Which is just a huge win. But if we extrapolate this methodology into the future, it leaves us with a fascinating theoretical problem.
Oh, for sure, because currently, ProLong relies heavily on human-readable formats.
Right. The environment outputs ASCII grids and text-based action logs, and the agent writes Python, which is a human programming language, to parse that human-readable text. We are basically forcing the agent to operate in our domain.
which, while effective here, is fundamentally inefficient for a machine.
Yeah.
If an agent can effectively write Python and regular expressions to query its own human-readable history, what happens when it begins optimizing the structure of that history itself?
What happens when the agent determines that parsing ASCII grids is computationally too slow, and it starts encoding its observations into its own bespoke compression algorithms?
Exactly. Instead of a logs.txt file full of text we can read, it builds a serialized database or a matrix that is entirely illegible to us, but perfectly optimized for its own retrieval.
So future agents could invent their own query languages, optimized entirely for traversing their specific latent spaces.
They wouldn't write Python to search text. They would execute alien scripts to search high-dimensional tensor representations of their past experiences.
Wow.
I mean, if an agent can already write regress.py to unit test a human-readable history, the logical next step is for it to discard the human readability requirement entirely to achieve perfect algorithmic efficiency.
An AI agent designing its own proprietary memory file format that we can't even decode, purely so it can navigate environments faster. That is a wild thought to leave on. Thank you for joining us on this deep dive into the ProLong paper. We will catch you next time on AI Paper Slop. Keep building and stop wiping your agent's logs.